morning to everybody, and thanks to the chair for the introduction. Biochemical monitoring of sweat analytes can be used as an index of health of people. For example, we can use it for personalized healthcare diagnosis or for improving the performance of athletes. For example, in the clinical side applications, we can see that it can be used for early diagnosis of health disease, or for example, for the monitoring the wound healing status. While in the consumer side applications, it can be used for wellness purposes, for example, for metabolic efficiency monitoring, or for electrolyte losses, for example, for define a personalized hydration program, or in the beauty industry. So by leaving aside the traditional methods for pH revelation, let's focus on the flexible on-skin pH sensors. Obviously, they should be small, flexible, and stretchable, and they have to avoid the presence of wire, so they have to be wireless. In other words, they have to be non-invasive and comfortable. So, in the last year, has been presented several works about these topics. For example, has been presented work about using the HF technology. This kind of technology led to have a small reading distance, but the advantage of this technology is that it uses few electronic components, while on the other side there are applications that led to reach higher distances. For example, by using the Bluetooth technology, but in this case we have more complex electronics because there are lots of components, and this kind of systems needs a battery because they are active systems. So the aim of this work is to investigate a technology that can be placed in the middle of this in this scenario. So the aim of this work is to use the UHF technology for enable a pH monitoring system. This technology uses the radiofrequency identification principle. So we have an epidermal sensor tag that works in the UHF band, and obviously it has a minimization of the number of electronic components, and the working principle is based on the best scattering principle. So the advantage of this technology respect with the Bluetooth are, for example, that it can be used in passive mode, so it doesn't need a battery, and for example, respect to the NFC technology, it allows to reach longer reading distance, and it can be used in one-to-many scenario. For example, I have only one reader, and I can interrogate more than one sensor. So it can be used, for example, for body sensor network. So the idea is to implement a lab on a Plaster where we have a chemical sensor, obviously, for the elevation of the pH, a sensor-oriented RFID IC, and finally a non-skin optimized antenna for the communication of the data to the reader. Let's start from the pH sensor. The sensor is made on a PET substrate. We can see a reference electrode, a working electrode, a counter electrode. The last one is used only for the deposition of the iridium substrate. So the pH sensor is screen printed as you can see in the figure. And finally, the iridium oxide film is electrochemically deposited by means of application of a potential of on the counter electrode. So the calibration curve of the sensor is shows linear behavior, and for the pH values of the suite for the healthy person is comprises from in a range of 300, more than 300 millivolt. And okay, the second part of the plaster is consists of a microchip with RF features, obviously, and on the sensing side, it has a 10-bit ADC converter for external sensors, and it allows to get to get the input voltage sensor, and as you can see, it's quite compatible with the tension, the potential given from the pH sensors. So, in order to have the full compatibility between the microchip and the pH sensors, a conditioning circuit is needed, because it needs to remap the sensor output within the input voltage of the IC, as shown in the slide. So, on the antenna was the IC has got some limitation on the antenna, because with this IC you cannot use loop or T-match configuration. So the principle is to use a 1 lambda dipole antenna, where I practicate some bent, and the key point of this antenna is that on the side branch of the antenna, the current flow in the same direction. So in this way we can maximize the gain of the antenna. So the layout, the device is a 3 by 3 centimeter device on a Kapton substrate. Here we can see a Mender line for achieve the in-phase condition of the current. Then we have a tuning inductor for the impedance matching between the antenna and the IC. On the bottom view, we have the conditioning circuit and the battery housing if you want to use the IC as a data logger. And in this area, there is the pH sensor. So, by means the CAD simulation, we can see that the currents on the side branches are in phase, but we can see also that there are some losses induced by the sensors, because some currents flows on the sensor and on the conditioning circuit, and that means that the reading distance could be affected by this behavior. So the prototype was fabricated by etching. Then the PET sensor was glued by an adhesive on the substrate, and finally it was coated and fixed with a breathable membrane over the arm of a volunteer. And from the plot we can see that simulations are in good agreement with the measurement marked in red. So, but for simplify the electronics of this device, a second generation of pH sensor was implemented. Before, I want to show you an example of pH measurement get by a real-time wireless acquisition. So as you can see, the voltage is correlated with the pH level. So we can see that the aim of this device has been reached. But in order to to simplify the electronics of this system, we have to build a second version of the pH sensor, and in this case we have to substitute the PAT substrate with the Kapton substrate, and with the same fabrication process, so the screen printing process. Here is shown the calibration curve of the sensor. As you can see, it has been translated. It has been up-translated with respect to the PAT curve, and it means that it's fully compatible with the range of the SL IC. But the last benefit of removing the conditioning circuit addresses also the reading distance of the IC, because from the same scenario we can see that the red curve is the PAT pH sensor reading distance, while the other curve is related to the Kapton pH sensor distance. As you can see, the distance has been doubled, and that means that the antenna gains more than 6 dB. And if you use this kind of device previously this measurement has been performed in the passive mode. But if you use this device in battery assisted mode, for example, for using it as a data logger, you can reach up to 2 meters of reading distance. For example, it can be used in a non-collaborative scenario. For example, when I pass through a gate, the gate can be downloaded my data, for example. So, in conclusion, an UHF pH sensor with an intermediate performance between NFC and Bluetooth technology has been presented, and the screen printed pH sensor over Kapton avoids the need of voltage preconditioning. That means that on the board there are only 3 components, and this device can be suitable to measure the pH of the sweat of the human skin. For the first future purposes, obviously there is the real-time experimentation with volunteers to evaluate statistics, reliability, and robustness of this sensor. So I have conclusion.